Welcome, ladies and gentlemen, to our final online lecture of the unit, taking a look at chemical properties and changes. So I went over a little bit on the last lecture where we had to take a look at how to separate mixtures, but part of that is because those separation techniques really focus on the distinction between physical and chemical changes. When you separated your mixtures, we didn't change what the things were. We took advantage of their physical properties to be able to separate them from each other. If you are going to break down a compound into simpler substances, such as elements, then I have to do that chemically. I am changing the chemical makeup of that substance. So a great comparison between that is looking at the changing water to water vapor as compared to the breaking apart of water into its component elements, which the next diagram shows quite nicely. So here, when we compared the two changes, if I simply look at water changing into water vapor, a liquid changing to a gas, I'm still looking at water molecules, H2O. They're existing in a slightly different energy level, there's a different state of matter, but I still have water molecules making up each of those substances. When I compare that to the chemical change, if I use a different type of energy, I can derive it through a chemical decomposition. So I do still start with H2O. So I did a little balancing there, which we will get to later in the year, but the point is what I finish with is a different chemical makeup than what I started with. I now have two elements as the product, instead of still having water molecules that I started with. So in the first, the physical change, I have a change in appearance or arrangement of the particles. With the chemical change, I've actually broken it apart and created new substances because the compound was broken down to create two individual elements. So if I'm looking at a chemical change, that brings in the idea of a chemical property. This one's tough because they're really close to each other, but they are different. So a chemical property is the ability to undergo a specific chemical change. So it's not the change itself, it's the ability to undergo that change. For example, if iron is able to oxidize and form rust, we would say that it has the property of being able to oxidize. So when you see that rusty old something sitting along the side of the road, it's because it's been able to create iron oxides when the water gives it the right conditions to form that rust. The only way to observe whether something can do this or not is to attempt to make it undergo the chemical change. So to determine that iron is able to rust, I have to allow it to do so to then observe the evidence that it has chemically changed from what it was before. So when I start to put together both my physical properties and chemical property data, that can allow me to have an easier time of being able to identify an unknown substance. So how will I know that a chemical change has occurred? I'm so glad that you asked that question. There's a lot of things that we can look for to provide evidence of a chemical change. One of the things is a transfer of energy. If you think back to our Flaming Dragon demo, there were several different forms of energy we identified that were released as a part of that reaction. What can make that tricky is if I look at something like freezing, the liquid water is releasing energy to solidify into ice. So we have to take into account more than one possible item. So freezing and becoming solid is not a chemical change, but it is a transfer of energy. So I have to look at more than just one of those properties changing. Now, a change in color is a pretty good option. The color of a substance comes from its chemical makeup and the way that light is reflected, refracted, or absorbed by the substance. So if the color has changed, there must be some new chemical structure that's providing that difference in appearance. Production of a gas. If I have some things coming together like it did in our observation lab at the beginning of the year, the two powders and the liquid, and we get a gas produced, there's a good chance that that is a chemical change. But what you must do is confirm that the gas is actually a different substance and not just boiling or a new state of matter. Now, in a similar idea, if I form a precipitate, which is a fancy science word for a solid, if I have two liquids come together and I get a solid that is created and you can see it kind of flaking out or settling out of the mixture, that is an indication of a new set of properties. That substance is now insoluble. So if a precipitate forms, you likely have a new substance that has new characteristics that are different from what the original substances were before the change. The real way we have to know, though, is we have to confirm that we actually have new substances formed before and after the change. So this brings us to the question of how do all of these properties and changes fit in with our classification of matter? So what we've come to is there are two main classifications of matter. You have your pure substances, which is going to be made of all the same types of particles, or you have your mixtures of substances, where you're going to have different types of proportions of things in there. So they are all physically combined. Whereas on the pure substance side, if it is a compound, then I would have it being chemically combined. Mixtures, because they are physically combined, can be separated physically using those physical properties, such as things like solubility, boiling point, particle size, that sort of thing. If I have a compound that needs to be separated, now I'm looking at chemical properties to see how I can break those things apart. In most cases, it's going to involve some kind of input of energy to disrupt that. Now, a chemical change could involve creating compounds from elements as well, so I don't just have to break them apart, I can also put them together. Because a pure substance is made out of all of the same particles, it will be homogeneous. A mixture, on the other hand, because it's not necessarily combined in any particular proportion, I can either have a homogeneous mixture that is evenly distributed, or I can have an uneven distribution. So remember that homogeneous, you should think your Kool-Aid. Every cup you're going to pour out of that pitcher, it should look and taste the same because all of the particles within it are evenly distributed. If you think of your heterogeneous mixture, think of this like your chicken noodle soup. Every spoonful you take out, maybe one spoonful you get a noodle, another spoonful you get a bunch of carrots. Since you're getting different samples out of your larger mixture, it's unevenly distributed and different parts have different amounts of the substances within the mixture. On a test or quiz, you should be able to classify a given example of something as either a pure substance or a mixture, and even in more detail, if it's pure, is it an element or a compound? If it's a mixture, is it homogeneous or heterogeneous? So be sure to use your example practice and your study guides to find more examples if you don't feel confident with that at this moment. That ends our lecture for today, so please make sure that your note sheet is completed, and we will be discussing next class.